Hello everybody. Let's start this chapter, that is the chapter equations of first order. Equations means differential equations. Over here we are dealing with ordinary differential equations. So ordinary differential equations of first order and first degree. So an ordinary differential equation of first order and first degree, it looks like that this kind of expression, that dy dx is equal to f of x comma y. This kind of expression, and sometimes this can also be written in this kind of form: m dx plus n dy is equal to 0. Now the question is that, can we always find the solution of this kind of differential equation? Can we always find the solution of this kind of differential equation? This is one differential equation. This is a different kind of differential equation in the same form. So can we always find the solution of this differential equation? Answer is, if it is guided by certain theorem that is called existence and uniqueness theorem, or if it is if it follows the conditions of that, if this differential equation follows the conditions of this theorem, in that case we can find the solution of this kind of differential equation, and the solution would be unique. But if these conditions of this existence and uniqueness theorem, these conditions are not satisfied, in that case we do not have any guarantee that there exists any such solution of this kind of differential equation at all. So we are just discussing the statement of this theorem. We don't require the proof of this theorem. The statement says that you see this f is actually a function of two variables. One is this variable x, another is this variable y. If this is a continuous function and along with that the derivative of this function f with respect to y, all right, derivative of this function f with respect to y, keeping x fixed, this kind of derivatives are called partial derivatives, and it is written by this kind of notation: del f del y. If this derivative is continuous, in that case we can have a unique solution of this differential equation. Actually, what would be the solution? If we try to consider this solution, over here y is actually a dependent variable. Y would be certain kind of function of x. Got it? So if we try to find the solution, geometrically speaking, it would be a curve in this kind of two-dimensional plane. This is x-axis and this would be our y-axis. This would represent a certain kind of curve, and if we try to impose certain condition like this kind of condition, y is equal to y0 and x is equal to x0, it means that the solution curve must pass through a point having coordinates x0, y0. Got it? Having coordinates x0, y0, and this would be the point having coordinates x0 and y0. Now through this point the solution y is equal to f of x will pass. You can consider not f, you can consider f1, because already f, this function, is provided. So in place of, instead of f, we are considering another kind of function, maybe f1. So this is the curve of the function f1. All right, the solution of this differential equation passing through this point x0, y0. So x0, y0, although it looks like a point in this two-dimensional plane, but it actually represents certain kind of initial or boundary condition What is the condition? The condition is that y is equal to y0 when x is equal to x0. Okay. So this is the existence and uniqueness theorem. The theorem says that the function f, this function of two variables, should be continuous. Along with that, this partial derivative of f with respect to y, this partial derivative must be continuous in certain region. Mathematically, we call it a neighborhood, but practically we can say in a certain region containing this point x0 y0, then within this region or within this neighborhood we have a unique solution of this kind of differential equation. Okay, this is called the uniqueness and existence and uniqueness theorem. I am not going to the proof of this theorem because it requires a lot of knowledge on mathematics of higher level. So I am not going through the proof of this theorem over here. So this is the statement of the existence and uniqueness theorem. Okay. Now, if this theorem, if these conditions are satisfied, then we can say that yes, there is a solution y is equal to some function of maybe f1, or you can also consider this as some function g of x. Y is equal to g of x, something like that. Now, how to find this solution? That is the next question. And in this chapter, we shall try to present different kind of technique by which we can find the solution of this kind of differential equation. And over here, this differential equation can also be represented in this form m dx plus n dy, where this m and this n, these are not always constants. You see over here, these are actually functions of x and y. Got it? So some function of x and y is there multiplied by dx. Again, some function of x and y is there multiplied by dy, that is equal to 0. Now let's move to the step by step. Let's move to the process of solution of this kind of differential equation. First of all, let me introduce the idea of two kind of solution, that is, these are called particular solution and general solution. First of all, let us discuss about this general solution. General solution is that whenever we integrate a differential equation, we generally get certain result with an arbitrary constant c. Now, in order to compute the arbitrary constant, we need to impose certain condition like y is equal to y0 when x is equal to x0. In this context, these are called initial conditions, but whenever in the higher study, whenever we shall deal with partial differential equation, then we shall have different kind of such conditions. One kind of condition is called initial condition, and another kind of condition will be called boundary condition, depending upon the context. I am not going through the detail because right now it is not required. So if we have a solution involving this kind of arbitrary constant c, involving this kind of arbitrary constant c, we may have more than one arbitrary constant if we have second or higher order differential equations. But over here we are only dealing with first order differential equations. So over here we are only dealing with this first order differential equation. That's why we have only a single arbitrary constant in this solution. Got it? We have a single arbitrary constant in this solution, and this kind of solution is called general solution. Now, whenever we compute the value of this arbitrary constant, what is the value of this arbitrary constant? In that case, we can use this kind of relation that y is equal to y0 when x is equal to x0. And after computation of the exact value of this arbitrary constant, maybe this value is equal to c0. So if you put c is equal to c0, in this form, in this expression, y is equal to pi of x comma c. If you put c is equal to c0 in this expression, then what we are doing, we are actually putting a particular value of c is equal to say c0. And how do you compute the value of c0? By the help of certain kind of initial condition. Then after putting that particular value of c in this general solution, what we get, that is called a particular solution. Okay. After putting certain definite value of this arbitrary constant or particular value of this arbitrary constant, then whatever we get, that is called particular solution. So particular solution can be obtained from this general solution, and there are other technique as well by which you can also compute particular solutions. So these are the main two category of solution that we need to discuss. And over here we need to discuss as per the syllabus. There is one kind of solution that is there is one kind of solution that is called singular solution. Singular solution. What is this singular solution? In the next subsequent lectures, we will discuss detail about this kind of singular solution. What is the singular solution? I am just introducing the definition over here. Singular solution is actually a solution which cannot be deduced. Okay, which cannot be deduced from this general solution by putting any definite value of this arbitrary constant c0. Apart from this particular constant, because you see, if you put c is equal to c0 in this general solution, we will get particular solution. But apart from this kind of particular solution, we have one more category of solution, that is called singular solution. Okay. Now, how to compute this singular solution? Does the singular solution exist for each and every differential equation? Answer is no. All the differential equations do not have singular solutions. There are certain kind of differential equations which have singular solution, and later on in the subsequent lectures we shall discuss special kind of differential equations for which singular solution exists, and in those kind of discussion we shall explain the detailed technique to compute this singular solution. Okay, so for this time being, I'm just introducing the definition over here, not more than that. So these are the definitions of three kind of solution. One is called general solution, another is called particular solution, and the third one is called singular solution. Okay. Now, how to find the how to compute the solution of a first order or first order differential equation? Let us going through few steps. First of all, you see, if this expression m dx plus n dy, if this expression m dx plus n dy, if this can be represented in this kind of form, differential of certain quantity, m dx plus n dy, if m dx plus n dy, m is a function of x, m is a function of x and y, n is also a function of x and y. For simplicity, we are just writing it as m dx plus n dy. Now, if this m dx plus n dy is represented as the differential d of certain function u, d of u, in that case we say that this differential equation is an exact differential equation, and we can directly integrate it. And what would be the solution? The solution would be is equal to u is equal to certain arbitrary constant c1, okay, or a certain arbitrary constant c. Superscript is written over here because there is a footnote related to this argument. So forget about this superscript. So u is equal to c. U is equal to c would be the solution of this kind of exact differential equation. You can consider this kind of examples as well. You see, twice x y dy plus twice y square x dx. You see, this expression can be written as differential of x square into y square. Hmm? So, as because this m dx plus n dy, this is the expression in the form of m dx plus n dy. This can be written in this form, differential of x square plus y square. Then what is u? U is equal to this expression x square y square. U is equal to this x square y square. So what will be the solution? Solution will be is equal to u is equal to some constant. The solution is u is equal to some constant. That's why the solution can be written as this u is equal to the constant c. So u is equal to c. So in this way we can compute the integral of a differential equation in exact form, and this kind of differential equations are called exact differential equations. But if you see, these were simple expressions. These are simple expressions, and by observation it was easy to compute the expression of this function u. But sometimes it becomes a bit difficult. If the expressions of m and n are becomes a bit involved or difficult expression. In that case, just by observation, it is very hard to compute the expression of this u. So in that case, how to check whether a differential equation in this form m dx plus n dy, how can we check that this is an exact differential equation? And the necessary and sufficient condition for such result is that partial derivative of m with respect to y, del m del y, that must be is equal to the partial derivative of n with respect to x, del n del x. We don't need the proof of these results. Over here, we don't need the proof of any of these theorems. We just need to apply these theorems in different differential equations. So let's discuss an example by which we can apply this result. By which we can apply this result on differential equations. So let's skip this proof and let's consider, just for the sake of showing an example, we consider this kind of differential equation: x square minus y dx plus y square minus x dy. So over here the coefficient of dx, that is equal to our quantity m, the function n. The coefficient of dy, that would be is equal to the quantity n. So m and n, these are equal to this kind of expression x square minus y, and n is equal to y square minus x. Now you see, if you differentiate this m, what was the condition of exact differential? The condition was that del m del y, that must be is equal to del n del x. So if keeping x fixed, in case of partial derivative, we just consider the variable y as the variable quantity, and the remaining variable other than y, because we are interested in the partial derivative with respect to y. So with respect to which variable should we differentiate, that is to be identified first, and that would be the only variable in that expression, and the remaining quantities would be treated as constant. This is the idea of partial derivative. So over here x square would be treated as a constant quantity whenever we consider this partial derivative del m del y. So del m del y would be is equal to -1. Similarly, in case of partial derivative del n del x, this x will be treated as the variable quantity and y should be treated as a constant quantity. So del n del x, that would be is equal to -1. If you consider this is the only variable over here, this x is the only variable over here, in that case derivative of y with respect to x, that would be is equal to this -1. Got it? So over here we find that del m del y becomes is equal to del n del x. So we observe that yes, the condition for solution of this kind of this kind of differential equation for exactness is satisfied. So over here the question was that Is this equation exact? The answer is yes. The answer is yes. Now, how to find the once we ensure the exactness, we know that there exists a certain function u. There exists certain function u. All right. Now, how to compute this function u? How to compute this function u? That we are going to show over here. For complicated expression, these 4 steps are given, but my advice would be that you please try to have certain observation power, because that observation power will help you a lot in to solve this kind of differential equation in most of the times. But if you fail to make to have such observation power, so that you can compute directly by observation, you can compute the expression of u. Because you see in this previous example, look at this previous example. In this previous example, it was easy to express, or it was easy to identify the expression of u. So if it is not easy at all for you, in that case, my advice would be to please go through these 4 steps. What are the steps over here? We have to integrate this first part. That means the function is given in this form m dx plus n dy. So we have to integrate this expression m dx, keeping y constant. We have to integrate it with respect to x. Then we need to integrate this second expression n dy. We need to integrate it with respect to y, keeping x constant. Now in this expression, in this second step, we have to delete those terms. We have to delete those terms which are already obtained in this step number 1. Let me show you this result by computing in detail. Over here, consider this expression x square minus y dx plus y square minus x dy. So this is our m. This is the function m, and this is the function n. M is equal to x square minus y. So if we integrate this m with respect to x, keeping y constant, what we get, you see, keeping y constant, we integrate this x square. What we will get? We will get x cubed by 3. All right. Then keeping y constant, so this y would behave like constant quantity. So keeping this y constant, if we integrate it with respect to x, we will get x multiplied by this constant y. So we are treating this y as a constant quantity. All right. So in that case, we will have this kind of expression x cubed by 3 minus xy. Now what we need to do? We need to integrate this n dy. We need to integrate this n dy, keeping this x constant. So if we integrate it with respect to y, this integral of y square will give us 1 by 3 y cube. And then integral of this constant x with respect to y will again give us this minus xy, and this minus xy term was common, that has been already obtained in this step number 1. Got it? So now we need to combine these 2 steps. What to do? We need to compute, or we can say we need to sum up the result obtained in this step number 1 and the result obtained in this step number 2, neglecting these common terms that we already had obtained in the first step. So over here, the third step would be just add these two expressions. The first expression is 1 by 3 x cubed minus xy. This is the first expression, and the second expression is 1 by 3 y cubed. So this is the second expression. So in this way, you can identify the expression of the variable u. And what would be the final solution? And the solution is also sometimes called primitive. Okay, so the solution will be u is equal to constant. Over here, this is the expression of u. So the solution is u is equal to this kind of constant. So in this way, you can compute the solution of this kind of differential equation whenever the differential equation is exact. Now see, is it clear to you? So far, কারোর কোনো জায়গায় কোনো কোশ্চেন আছে?
Sir, I have a question, sir.
Yes.
So suppose we are given an equation and which is inexact, and then how shall we solve it, sir?
I am coming to that questions, but so far I am restricting my discussion to the exact differential equations, and I am just asking, is this much okay? I shall deal this question later on.
Okay, sir.
Because most of the differential equations are not exact. Yes,
okay,
you please
sir.
Continue.
Sir, x cube plus y cube minus 3xy equal to k is the final solution of that equation.
Don't ever say final solution. There is no such final solution. The technical term is that either you get general solution, or you get particular solution, or you get a singular solution. Okay. So over here, this c is an arbitrary constant, and what is k? K is equal to 3 times of c. So over here, this k, you can consider this k is also another arbitrary constant. So you see, in this solution we have an arbitrary constant. So this would be the general solution. Got it? No such final solution is there. You can say this is a general solution. Now from this general solution, you may, if you put certain particular value of k satisfying certain initial condition, in that case you will get certain kind of particular solution. So don't ever say this is the final solution. This is a general solution. Is it okay?
Okay, sir.
Any other question? Any kind of question? No question. Okay, so this was the first technique that I wanted to discuss in this class, when the differential equation is exact. But the problem is that very few differential equations are exact. But as a starting point, we discussed this kind of exact differential equation. Now let's move to the differential equations when the differential equations are not exact, and what to do. Over here, some other examples are also provided. You can go through this kind of examples, and you see this is the first step-by-step technique that I have demonstrated earlier. And in this second method, this method number 2, they have just used this kind of grouping technique, just by identifying that yes, it might be that cos y dx and x sin y, these two together can be written in this form of differential of certain x into cos of y, and similarly the remaining terms can also be written as the differential of y into sine of x. So by observation power, we can identify or integrate it, and we can identify this expression of u. So that is also demonstrated over here. And if we try to separate or segregate similar terms, most of the times it will be able to compute the expression of this u, of this function u, so that you can easily compute the solution or the general solution for this kind of differential equation. And that requires a lot of practice. And over here, many such differential equations are there. Most of them are, I think all of them, if you do not have any printing mistake, in that case all of them are exact differential equations. You can go through these differential equations for your homework. Answers are also provided. Now I am going to discuss the second kind of differential equation that is not exact. If the differential equation is not exact, then what to do? Then we try to multiply this kind of differential equation by certain function of x and y, so that after multiplication we can consider we are multiplying this differential equation by certain function mu. Generally we simply designate it by mu, but mu is actually a function of x and y. All right, mu would be a function of x and y. Just for simplicity, we are designating this expression, this function as mu. Hmm. So if we multiply a differential equation by certain function of x and y, and if after multiplication the resultant expression, that would also be a differential equation like this, mu into m dx plus n dy. If this resultant equation, if the resultant expression becomes exact, then such function mu, this kind of function mu is called integrating factor. This multiplication factor is called integrating factor. Why integrating factor? Because it helps us to integrate, or it helps us to convert the differential equation into a form which is possible to integrate. Otherwise it was not possible previously, but over here after multiplication by this kind of factor, this differential equation ultimately converts into a form which is exact, or which can be directly integrable. So this kind of differential equation, this kind of multiplication factor is called integrating factor, or in brief we designate it that as I dot f dot IF, or integrating factor. Got it? So the problem now reduces to find the, as a first step we need to find the integrating factor, and the second step is that after computation of integrating factor we shall seek the solution of the differential equation. But you see, the problem is that whenever we have a differential equation, in most of the times, although in your syllabus we are dealing with easy category of differential equation, that's why after multiplication of this kind of integrating factor mu, we are able to compute the integral or the solution of this kind of differential equation. But in most of the times in the practical field, whenever we generally make our research, in this kind of practical field, it is very hard to find the integrating factor. And if it is, even if we can find certain integrating factor satisfying the condition of integrability. What was the condition of integrability? I told you that the condition of integrability was this kind of condition, del m del x. This one. This was the condition that del m del x, del m del y is equal to del m del x. So this was the condition for integrability. But okay, fine, we satisfy this condition. But how to find the solution of this differential equation? That is very much challenging job. And whenever we find a differential equation, most of the times we cannot integrate them by proper functions, because maybe we do not have certain functions known to us, which would help us to integrate them. Maybe may not. You see, we have a very limited number of functions in our hand, like trigonometric functions, or exponential functions, or algebraic functions, maybe logarithmic functions, and all. Sometimes hyperbolic functions are there, and many mathematicians have developed several kind of similar functions like elliptic functions and all. Elliptic functions were developed depending upon the process of integration. But over here, physically speaking, you see, a physical system generally always satisfy mainly two category of equations. One is either differential equation, and another kind of equation is also there, that is called difference equation. either differential equation or difference equation. And differential equations are also studied similar to differential equations. And the problem is that whenever we integrate a differential equation, we get an arbitrary constant like c. And there is a theorem in mathematics, especially it was developed by the mathematician Noether. It is called Noether's theorem. The theorem says that this kind of arbitrary constant, hmm, whatever be the number, maybe 2, maybe 3, or maybe 4, if we have in nth order differential equation, then in order to solve the differential equation, we need to integrate it n times. Okay, if we have nth order differential equation, then in order to find the solution of that equation, we need to integrate it n times, and for each such integration, we shall get one arbitrary constant. And Noether's theorem says that this kind of arbitrary constant always represent certain kind of conservative quantity in the system under investigation. You have the idea of conservative quantities, like you see in a physical system. Sometimes if a system is conservative, sometimes the total energy of that system is a conservative quantity. Sometimes momentum conservation law is there, and different other kind of conservation, mass conservation law is also there if it is not a problem of having mass. Hmm? So different kind of conservation law we encounter in physics, but we have very little conservation laws, and that much conservation law, or that equivalently speaking, that much constant will not be sufficient for the integration of an nth order differential equation. So you see, if a system is there, if a system is guided by, say, third order differential equation, and in that system, if we have only two quantities, maybe momentum, maybe the total energy, if we have only two such physical quantities which are conserved, in that case, it would never be possible to integrate the differential equation. That is a kind of explanation in terms of physics or physical laws. Got it? So in such cases, what we do, we had to follow certain other technique, and that techniques are called numerical techniques to solve this kind of differential equations. That's why this kind of differential equations become much more harder whenever we deal with higher, second or higher or third order or fourth order differential equation. That integration process becomes much more difficult and involved, as far as the mathematics is concerned. Okay. Anyway, so let's move to the solution technique. Whenever we got, whenever we get certain integrating factor. Now the question is that how to obtain such integrating factors. We shall discuss in detail about the integrating factor. But over here, let's go through few examples for today's lecture at least. Suppose we have this kind of differential equation. Now, you see over here x dx plus y dy. This expression, this expression x dx plus y dy. This expression is easy to integrate because this can be written as differential of half of differential of x square plus y square. And now you consider this expression x dy minus y dx divided by x square plus y square. X dy minus y dx divided by x square plus y square. Now numerator and denominator can be divided by x square. So after some manipulation, this expression can be written as differential of tan inverse of y by x. So in this case, the equation is easy to integrate. But sometimes you see these differential equations are not easy to integrate. Over here you see it appears that we are not multiplying anything. We are not multiplying these differential equations by anything at all. Now look at this example, this one. Okay, over here this expression y dx plus x dy, this can be expressed as differential of xy. Now you see this is the problematic part, x dy minus y dx. If we divide this expression by x square, then only we can express this expression, that means x dy minus y dx divided by x square. We are dividing this one by x square, dividing this one by x square, and after division we would be able to express this expression as a differential of y by x. So division by x square means we are multiplying this expression by x square. So division is also kind of multiplication. So over here it may appear that yes, we are not multiplying, rather we are dividing. But over here, if you carefully observe that this expression y dx plus x dy has been written as differential of x into y. And after this, after division by x square, this expression, or in other words, we can say after multiplication by 1 by x square, this right hand side expression can be now written as this kind of exact differential of y by x. Got it? So 1 by x square is a kind of multiplicative factor or integrating factor. Got it? So in this way, after multiplication by 1 by x square, we are now able to integrate this one, and in that case we get this kind of final, after the integration we get this kind of general solution. Over here this is the general solution because it involves an arbitrary constant. Okay, and there's a few other examples as well. You can go through this example, and there is a table that is provided over here, just so that you can easily identify the integrating factors. Suppose the expression is this kind of expression is there, x dy minus y dx, this kind of expression is there. In that case, sometimes 1 by x square becomes an integrating factor, so that after multiplication by 1 by x square, x dy minus y dx would become is equal to this kind of expression, and that is nothing but the differential of y by x. But sometimes we, depending upon the problem, we need to multiply this expression by 1 by x square plus y square. So that you see this expression and this expression both are same expressions, but the integrating factor might be different depending upon the other terms involved in that differential. Got it? So over here, multiplying this expression by 1 by x square plus y square, what we get, differential of tan inverse of y by x. So this table will help you to identify certain integrating factors. You can please go through this table, and you can go through these examples as well. This will help us to understand how to identify different integrating factors. And remember, this is very first-hand advice, because there are other techniques by which we compute integrating factors. And you see over here, sometimes we are multiplying this expression by 1 by x square, sometimes we are multiplying this expression by 1 by x square plus y square. So you see, integrating factor of a given differential equation is not always unique. You may get two different kind of integrating factors. You and your friend may get two different kind of integrating factor, which would help you to integrate the differential equation, so that you get different kind of general solutions. So that is the main objective for this lecture today. I wanted to introduce the idea of integrating factor, and you can go through these examples, these two examples. I'm keeping these two, this exercise number 2b, and previously I left one more exercise. So you can go through these examples as the. I'm just keep leaving them as the homework. So that's all for this lecture. Thank you for being with us.